Okay, so problem 20.36 actually requires that you do problem 20.34. And the reason is because in problem 20.34, we have a data set with an outlier. And in problem 20.36, we're going to do the same evaluation we do for 34, but we're actually going to remove the outlier to see what the effect of removing that outlier would have on our confidence interval. So here we have the problem, the original problem from .34, and these are measurements of the angle and degrees of deformity of 38 consecutive patients under the age of 21 who have this condition called HAV. And you can see that they've given us the sample size, which is n equals 38, which is right here. And they've given us the data, which is here. And they ask us a couple questions. They ask us, one, is it reasonable to regard these as these patients as a random sample? And the second is to figure out what the 95% confidence interval is for that mean angle in the population of all of these patients. So we're being asked to give an interval with 95% confidence. So let's conquer the first part of this question. Is it reasonable to consider this a random sample? So there's two things you want to look at here. There's a few things. Is this a bias? Is there any bias introduced in this sample? And I would argue that no, there's no bias. They actually took 38 consecutive patients, which really means that there's no other conditions that they were accepting these patients, and there was no external bias. It wasn't that they were only picking certain patients that looked more deformed than others or anything like that. So it was just whoever walked in the door first was the next patient or the next next individual in that sample. So the next question you want to ask is, what about the data itself that we've collected? So let's look at the data here. So the data is interesting because we have an outlier, and if you do a stem plot, you can clearly see that the outlier is at 50. That's the outlier. If that 50 wasn't there, we'd actually have a nice, almost normal curve, maybe skewed a little bit to the left, but overall, a pretty normal curve. But this outlier definitely creates different dynamics. And so the outlier is important. It's important to note that there's an outlier there. So now we're actually going to look at this confidence interval. So I'm given certain pieces of data. I'm given the fact that the sample size n is 38. I'm given the fact that this is a random sample, and I'm also given the confidence level that I'm shooting for here as far as the confidence interval is concerned. So and I'm also given the data. So if I put the data into a spreadsheet program and I calculate the average or the mean, which in spreadsheet programs is called the average, the function is called average, I will get a value of x bar being 25.421. I know my degrees of freedom here is going to be 37 because it's just n minus 1. And I can also calculate the standard deviation of the sample by plugging this into software as well and getting 7.475. Now, if you're still struggling with how to do this in software, you click in a cell, you select, you click type equals, and then type average, and usually it will auto-complete for you. And now I'll just put some range of cells. So in my case, it might have been A1 to A38 is my cell range that I'm looking at, the numbers that I'm looking at. It's likewise with standard deviation, if I do STDEV dot S for sample, because we're working with a sample, not a population, and I can actually use the same range, and those should give us these numbers. Now I've rounded to the thousands, but roughly speaking, you should get something close to that. So now the last thing I need to know is, well, I'm looking at a confidence interval, I need to know what my critical value is. What's that magic number, that multiplier? So if I look over here at my t-table, here's my 95%, and now I need to find the degrees of freedom. Well, I have a 30 or a 40. There's no 37 in here. And so if I, kind of work down here, I can see that the number is somewhere in here, between 2.042 and 2.021, but it's not exact. So I can err on the side of caution and go with the 30. I could take the average between 30 and 40 and use that because it's 37, so maybe it's a little higher than 50% of the way. But the other thing I can do is just use software. So let's just work through the software side of it. Now to think about the software side, we actually need to think about what it is we're looking at here. So I'm just going to draw a normal curve here. And we know what the mean of our data set is, our sample. This is x bar. What we don't know is, with 95% confidence, what is this range that values could fall in if we were to pick another sample, for example. So we don't know what this is. But this is 95% here. And we don't know these. And we don't know if we pick something outside of that, something over here, we also don't, what's the probability that it's going to fall on the outside? So essentially what we're looking at is, we're not looking at one side of this or the other side. We're looking at two tails of this. Even though we're looking at the 95% confidence interval, which is in the center here, we really need to sort of flip this around and think of it as we're looking at these two pieces here, which is 0.05 or 5%, the 5% that we're missing. So when I go back to my software, I can actually use a function called tinv. Sometimes it's inv or t.inv. And what it's going to ask us for is a probability. And so we'll put in 0.05 because we're looking at the tails here. And we need a degree of freedom, which in this case will be 37. If you plug that in, you should get a t somewhere around 2.026, or a critical value. So that's the critical value that we're looking for. So now I can do everything. I can plug everything into my interval, my confidence interval formula. So x bar plus or minus t star times standard deviation over the square root of the sample size. And when I do that, I should get 25.421 plus or minus 2.026, that's my critical value, times the standard deviation, 7.475, divided by the square root of 38, excuse me, the sample size. And I can work through the math here. I'll just work one side of this just to keep things simple. So I'm just working out the math here. And this becomes 2.026 times 7.475 divided by the square root of 38, which is 6.164. And now if I do the division here, 2.026 times these two numbers divided by each other is 1.213. And now if I multiply these, I should get 2.457. So what that's saying is that if I take this number now and plug it back in here, I'm saying that it's the mean, 25.421, plus or minus some margin of error here, which is 2.457. And what that translates to is that I have this range of values, and if I add 2.457 to this number here, 20 to the mean, and I subtract 25.421, 2.457 from 25.421, I should get a range of 22.964 to 27.878. And these are degrees because that's what we're measuring in. And so this is the range. This we just solved for these guys here. So 22.964 and 27.878. So I can say with 95% confidence that the mean, if I take another sample, is going to fall between these two values here. Now in 20.36, they remove this outlier. And so what ends up happening is your number of samples goes down by 1. So now you have, instead of 38, you have 37. Your degrees of freedom goes down by 1. Now you have 36 degrees of freedom. Your X bar changes. It becomes a lower number. I believe it's 24.757, somewhere around there. And your standard deviation will change. That'll become a lower standard deviation, a smaller deviation, because that outlier goes away. Your T star will also change because your degrees of freedom have gone down a little bit. So this number will become slightly smaller. So it's 2.026 is what, I'm sorry, it becomes slightly larger. 2.028 is what you end up with when you recalculate, so 2.028. This number here, the X bar became 24.757, and the standard deviation is 6.339, I believe. So all these numbers change, which means that this formula here, actually the numbers here change as well. And so if you plug all of these new numbers in and you do all the calculations, what you end up with is a range of 22.644 to 26.87, I believe. That range is actually a smaller range than what we were originally, what we got when we did the original problem, 20.34. And the reason is because we got rid of that outlier. So this is with no outlier, and this one is with an outlier. And because we got rid of that outlier, we can actually improve our confidence interval, because that outlier isn't skewing the data overall. And so if we have outliers like the ones we had in 20.34, it actually gives us less confidence over a small range of numbers. So we actually increase the range in order to get that 95% confidence.